Welcome to the... Oh, okay. Good afternoon, everyone. Welcome to the session about reactive programming. A little bit about myself. My name is Georgi, and I'm a software developer, obviously. And I have the privilege of learning from and working with Eric Meyer. And today I want to convey a little bit of my enthusiasm and knowledge about Rx to you in this session. So by the way, I don't have a Twitter account, but if you're interested in information about Rx, just follow that Twitter head in the box. Also, I cannot really see a lot because of the lights, but if you have a question, just raise your hand, and if I don't see it, just scream or do something to draw my attention, and we will address your question immediately. So let's dive in. We have quite a comprehensive to-do list for today. So let's start off immediately, but before we start, I have one word of warning. If you go around on the internet, Google a little bit, browse a little bit, on the topic of Rx, of course, you will notice that there are a lot of tutorials, videos, talks, presentations that are very interesting, very worthwhile watching. But there is one slight problem. A lot of them state that Rx is basically functional reactive programming. Now, I want to clear that up right now before we start. Rx is not functional reactive programming. I won't go into details of the differences here, but functional reactive programming, the main differences is that FRP deals with continuous time, whereas Rx deals with discrete time. And if you're interested in more differences, please talk to me after the presentation. So let's ask ourselves the question, what does reactive really mean, right? What do? We ask the internet. So we browse, we Google, and we find very general terms about describing our reactive. So event-driven, scalable, resilient, responsive, and even elastic. I'm not even sure what elastic really means, and these are all really very terms that I, as a developer, I'm not really sure what I must do with them. They don't really clarify the concept of reactive for me. So what do? We turn to some smart people. Apparently, in 1989, when I was 2 years old, a smart man called Gerard Berry formulated a difference or a distinction between several types of programs. And namely, he mentioned there are interactive programs. Now, interactive programs are programs that maintain a continuous interaction with their environment, which can be users or programs or whatever. And they do this, they maintain this interaction at their own speed. So the speed of operation is really determined by the program itself. That's an interactive program. Then he stated that reactive programs are actually also maintain a continuous interaction with their environment, but they do so at the speed which is determined by the environment, right? As opposed to the program determining the speed. The environment is now determining the speed. Now this, for me, is already a bit more concrete, right? What reactive might mean. So now let's ask ourselves the question, what is Rx? So we browse to the GitHub repository, go to the wiki of, say, RxJava, and we see immediately the first sentence. So let's zoom in on this first sentence. It says, Rx is a library. Is the mic? Yeah. And it's a library for composing asynchronous and event-based programs. All right. And it does so by using observable sequences. Now, what are we really talking about here? Composing asynchronous sequences. Now, I don't know about you, but my non-reactive brain currently is popping up. There are all sorts of questions popping up. So I see this word asynchronous. I'm already afraid, right? Because asynchronous programming in this day and age is still very difficult. We have a lot of problems handling asynchrony, concurrency, etc. So raise your hand. Who has ever experienced the situation called callback hell? I see a lot of hands, as expected, of course. Like, for those that haven't experienced it, it's a situation in which you have callbacks inside of callbacks inside of callbacks, so a deeply nested structure in which the control flow is unclear, you don't really know what's happening, and you're even afraid to change a single line because everything might just break. So I guess Rx will help us in that regard somehow. Well, we'll see. Then there's this word composing. Now, composing, I mean, that comes from compositionality. I find that to be a really beautiful word, compositionality, right? I guess Rx allows us to compose our programs, our asynchronous programs, like sort of like an artist, like a musician maybe. But we'll have to see whether that is the case or not. And then the word sequences. Now, sequences, as a developer, I know sequences as collections, right? That's the way I usually consume sequences. So what does this mean? Is our asynchronous and event-based program, are they somehow now exposed to us in the form of collections? And if so, can we regard them in the same way? Can we do we have the same operations that we're used to on collections? Well, these are some of the questions that I will hope to answer in this talk. And in fact, the most important word in this sentence for me is actually not highlighted, namely observable. And that might not make a lot of sense right now, but after this talk, I hope it will be very clear why observable is the most important part of this sentence. So a little bit about the background. Rx was initially implemented for the .NET platform, rx.net, by Eric Meyer and his team at Microsoft. And it was very successful. So successful that actually Netflix decided to adopt the paradigm. Now, Netflix was very JVM based. So what they did was, instead of porting everything to .NET code, they just rewrote the Rx library for the JVM. So they wrote RxJava, and on top of that implemented Rx Scala. So in this talk, I will mostly be using exclusively be using Rx Scala. So who here isn't familiar with Scala syntax? All right. I will try to explain as much as possible as we go along. But the ideas, the general ideas and the concepts are pretty much the same in all the Rx implementations that you will use, or might use. So remember when I said Rx is not FRP? If you're really inclined to put Rx in some kind of box or give it a general term, I suggest we use complex event processing. I think that fits the library a lot better. All right, so let's dive in. What are we talking about? This is the table. So we as developers, we as programmers, when we do our day-to-day job, when we write code, we more or less, in a general sense, encounter 4 different situations in which we do or want to do computing. The first is when we want to do a computation which results in a single item, and we want to do that in a synchronous manner. How do we do that? Very simple. By a simple function call. We call a function, say, getItem. This, we wait for it to finish, so we block. And then once it's done, we get a result of, say, type T. All right. Now, what do we do when we want multiple items in a synchronous manner? Well, that's the iterable that we all know, we probably all use. So we call the function getItems. This gives us an iterable of type T, right? To this iterable, we can ask for an iterator, and then we can start pulling out one by one items of type T. So on each pull, we basically block. That's why it's synchronous. We wait for it to give us the type T, and then we handle it however we want. So it's synchronous because we're blocking. Now, what do we do if we want an asynchronous computation which results in a single item? Well, instead of just returning a type T, now we call getItem async, just a name, and that returns a future of type T. So a future is more or less like an IOU. It's like we don't block. We receive the future immediately, and once the result of the computation, the value of t, becomes available, then we react upon it. Then we do something. So we will look into that a bit more. But what do we do for multiple items in an asynchronous manner? That's really where Rx steps in. So, but before we dive into that, let's take a step back and look at the future. So, like I said, the future is a non-blocking and an asynchronous computation. So we don't wait until this function or this computation actually has a value. We just call it, it starts computing, and then whenever the value is ready, we react to it. So that value, the actual value, may become available at some point in time. Now, a future might either actually complete successfully, in which case we will actually get the value of type t, or in the other case it might fail, so then we have to react upon a failure. Now, the nice thing about the future is that in the type signature of your functions, in the type signature of your data structures, it makes the effect of latency and the effect of asynchrony explicit. You immediately see that a function that returns a future probably has some latency. That's why it's a future, right? So we don't want to be blocking it. We just go on with our lives when we call it, and whenever it's done, we react. And it also tells us that, obviously, it's an asynchronous computation. Now, and this may not make a lot of sense yet, but bear with me. We can actually view futures as a collection which emits 0 or 1 element. So let's look at an example of how to use futures. This is basically from the Scala documentation. And what we see here is that we have a function on a session object called getRecentPosts. And this goes over the network, has high latency, and we don't want to be blocking and waiting for it. We just want that to be handled, and once it's handled, then we do something. Otherwise, we just go on with our lives. So this returns a future of a list of string. And what we do is, on this future, we register 2 callbacks. One, what happens when the computation fails, and another one, what happens when the computation completes successfully. So this is a very simple example here. We just print the error and print the posts. But this is more or less the idea of how to use futures in a very simple way. I don't want to dive too far into the futures. The only thing that I want to say is that they're all nice and well, but once you start to use them for multiple items, it gets quite complicated, because now you have to use futures of lists of futures or some kind of combination of that, and composability is really nowhere to be found. So let's go back to our table of the 4 effects and look at what Rx has to offer for us for asynchronous computations with multiple items. Well, an observable, like I mentioned before. So you have a function, getItems async, and this doesn't block and returns immediately an observable of type t. And we can view an observable of type t really as a stream of events that happens asynchronously, and nothing really blocks, only when items get emitted. So let's take one step back another time. So, in fact, the iterable that we were talking about earlier, that really implements a pool model, right? It's a blocking computation every time you pull something out of the iterable. It's synchronous because you do that one by one. And in fact, from the consumer's point of view, the consumer is really in charge, right? You just take one, another one, and you wait. You can't really take the 5th one and then the 3rd one, right? It's all synchronous. And now, as opposed to that, we have the observable, which implements the push model. Now, think of this situation from the consumer's point of view. The consumer here really has no saying as to when items get emitted. It's all asynchronous. It's also really non-blocking because, it can't really do other stuff. But the idea is really that from the consumer's point of view, the producer is in charge here. Right? The producer is producing these values, and the consumer has to just consume them. right? It has to react upon these items whenever it gets them. All right, let's look at this push versus pull model then. So as we know, we have iterators, and I've showed you that is the pull version, and then the observable version of an iterator is an observer, and that's the push version. Iterator, if we look at it, has a function next, right? So we call next, we block, we wait, we get a function of type t. Now observer, on the other hand, we pass in a function on next. So that is what will happen whenever something of type t gets emitted. In the case that something goes wrong, an iterator more or less throws an exception. For the observer, we pass in a function on error that takes an exception and then does something with that. Iterator, well, once it doesn't have any values anymore, so has next, then it basically completes. And for the observer, we again pass in a function called onCompleted that knows what to do when the stream is done. So maybe we should add the types to these functions. Let's look at how they compare. Iterator's next function is a function that takes, so for the non-Scala people, this empty tuple, that's basically, you can see that as void. You know, it takes no arguments and then returns something of type t. Now, observer is exactly the opposite. It takes something of type t and then does something but doesn't return a value. For the case of failure, iterator, you can generalize that to a function that takes nothing and then returns an exception. In the observer case, we see that it is a function, usually we call that a lambda, that takes an exception and again does something with that exception, handles the error, whatever it has to do to react upon that. Now, iterator, once it's done, so for the completed event, we see that we can model that as a function that takes nothing and returns a Boolean. So we can ask, are you done? Are you done? Are you done? And for the uncompleted, it's more or less the same. So here is we pass in a function that takes a Boolean, and then it can detect whether or not the stream has completed if the Boolean is true. But there is a slight difference in reality, because this Boolean is actually not really necessary, because in the case of observer, this last function will only be called once it's completed, right? So we can change this type signature to just unit to unit. But that was just to show the duality of these types and the niceness. Now let's look at the higher type, iterable. What is that in essence? Now, iterable is just something that has a function called iterator, right? You give it, again, no argument, and what you get back is an iterator of type t. Now, in the observable form of this is subscribing. So observable has a method subscribe. You pass it a lambda that takes, a function that takes an observer of type t and then does something, whatever is necessary on this subscription. So let's look at these observers. We have seen these types, and they really correspond to the implementation actually. So this is directly copied from the library. This is the real code how the observer trait is defined. And for the non-Scala people, this is more or less like an interface with implementations. So so what we see here is that the observer type is parameterized over t, and it has three functions: on next, on error, and on completed, just like we have talked about. And the interesting thing is that it has three empty function bodies. And the reason for that is that you can observe something without actually implementing these functions. You can implement 1, 2, 3, or 0 of these. So this is basically, the default implementation is just to do nothing. Just subscribe to the stream and do nothing. All right. Now that we know what an observer is, just three functions, let's see how we can subscribe. Now, we have an observable. Simply we call subscribe on it, and we give it an observer. Actually, that semicolon in Scala is not necessary. But what I personally prefer to do in practice is not first instantiate this observer object, but just pass in these 3 lambdas immediately, right? Because we can just pass in a lambda that handles every item that is emitted, a lambda that handles the termination with an exception, and one when we complete naturally. Also notice that when we subscribe to the observable, the thing that we get back is a subscription. All right, then. What is a subscription? Another trait, quite a simple interface that we can use to check whether or not we are still subscribed to the stream. And we can actually, as an observer, we can say, you know what, stream, we have enough. We had enough, we don't need any more items, just unsubscribe me. So that is the subscription. Now let's look at this in a bit more visual terms. I must say I'm not really a UML fan. I don't use UML a lot. I do not claim this to be UML. These are just ellipses and arrows. So don't kill me if some UML thing is not correct here. But the 3 types that we have seen are observable, observer, and subscription. So to visualize their interactions, an observer can subscribe to an observable. At that moment in time, immediately, right, we don't block. We return an object subscription. And from that moment on, the observable can start sending items of type T or an exception or a completed event to the observer. And then the observer can use a subscription to unsubscribe itself from the stream to tell it that, you know what, I had enough. All right, so we have seen how to create these observers with 3 functions. We have seen how we get the subscription, right, by subscribing to the observable. Now let's see how do we create observables. So observables in the Java version of Rx, you would call a factory method called observable create. Now in Scala, what we do is we have a companion object for the class observable, which has an apply method, which we can call implicitly, so we don't have to type in the name. It's just for, we're all lazy and such. So, but the basic idea of this factory method is that it takes the function which takes an observer and then returns a subscription. So this is what we call the unsubscribe function. This function will be called every time a subscriber subscribes to the stream that is exposed by this observable. All right, now, okay, that's fine. This is the definition. How do we use it? Well, very simple. In Scala, we just call this apply method and give it a function that takes an observer. And then on this observer, we can call those 3 functions that we were talking about earlier. So we can call on next, send in a number, and then call on completed, and this obviously is a very simple stream, just emits a number and then it completes immediately. Now for a little bit more involved example, let's say we want to create an observable of books. Now that takes a function that, again, takes an observer, and we try to emit a new book and then complete, and if anything goes wrong, we just catch the error and propagate that error to the observer. Right? So what we do is just call on error, and then the observer can deal with this error, however he likes. All right, so now that we have seen this more or less, let's look at some code. Here I have my IDE. For now, ignore the commented code. I want to show you just some simple examples of creating these observables. So here, is this visible in the back? Yes? Okay, perfect. So here we create a source, which is a factory method called observable.empty. Well, empty is more or less what the name suggests. It doesn't emit any items. It just completes immediately on subscription. So what we do here is we subscribe to the source, and like we said, we pass in one function that takes an element v, then prints it. then another function which takes an exception and then prints the stack trace, and then another function that takes an empty tuple, also known as nothing, and prints done, right? So if I now execute this, what we will see on the terminal, done. Well, surprise, surprise. So notice also that I have added a read line to the end of the program. Now the reason for that is that if I wouldn't do this, there is a high chance that since nothing blocks in this code, that the program would just fall through, right? And before we even get a chance to emit the uncompleted event, the whole program would already stop, right? The JVM would kill the program because nothing is blocking it to do so. So let's look at the second example. Here we create an observable of error. Well, again, does exactly what the name describes. We pass it an exception, and all it does is emit one error. So now we run this, and no surprises there. We see that the exception has been printed by this function. All right. Now, the next example is a bit more interesting, I would say. So here we have observable.just, and this is basically like a var args parameter that we pass in. So this can be comma 4, comma 5, whatever. And these can be any types of objects. They just have to be of the same type, right? Because we're type safe and we have observables of type T, not observables of anything. So this emits 1, 2, 3, 4, 5. I hope, and then prints done, because now we have emitted 5 items. On next of the subscriber has been called 5 times, and then the print function. All right. Now another one, and this might surprise you, but this is an infinite observable, observable.never. It actually, well, again, the name says it all. It never does anything. It doesn't emit an item. Oh, I'm sorry. Why did I? So this doesn't emit any items, and it doesn't error, it doesn't complete, it just goes on forever and ever. Now you might think, why is that useful? Well, in practice, actually, it is very useful. Again, we can do from a list, and I won't run this one, so this just takes the list and then emits every item. Well, you know what? And all right, hello world, and done again. And here comes a more interesting one. So interval. Now we want a timer that emits a time tick every half a second, right? And that's it. Observable.interval, and now we have a stream of events that every half a second emit a time tick. So let's run that, see what happens. Compile 1, 0, yeah. There it is. Every half a second it just emits a pulse. So, right, now this is the example that we have seen for emitting just one value manually, basically. Just so this actually uses the observable apply companion method. In Java, you would do this as observable.create and then pass in the lambda. So that's basically the same factory method. And this just emits 42 and completes. There it is. All right. Now for a more involved one, here is one that emits 3 random numbers. And after that, it immediately completes. So let's look at that. Now notice that I've wrapped this in a try-catch block, which will propagate the error through to the subscriber. But obviously no error has occurred. Now let's look at what happens if an error does occur. And there it is. Oh, sorry. It emitted 3 items, then it threw the exception, and then it didn't execute the uncompleted. Now the reason why it didn't execute that will be explained a bit later, but there's a good reason for that. All right, so now you have seen how to create observables in a very basic way. But now you might be wondering, so, okay, you were talking about callback hell and nested callbacks and whatever, but how does this really, we're still working with callbacks, we're still passing in functions, and how does this really solve callbacks? Does it solve callbacks? I don't know. So the question is really, what does Rx give me as a developer, as a program? What do I get out of Rx? Well, the first thing, yes?
Just a question out of curiosity. The interval you showed us,
Yes?
can it be implemented, or is it maybe implemented in terms of from list where you have an infinite list that does the waiting? Or
That
is it completely not, is the implementation completely not related to the from list?
I don't think the implementation is related to from list, so the question is whether or not the interval operator is implemented using from a list function. Personally, I don't think so, because you also need to wait for certain times. You could do that in thread.c. I'm not sure about the real, the actual implementation. I would guess that there is just a simple loop running. You don't really need the extra overhead of creating the list or the iterable, right? So, but we would have to check the code to verify that. All right. So, what does Rx give me? Well, one of the nice things is now that having these observables, right? These observables represent event streams. And now we just have them as first-class citizens in our programming language, right? Just by using this API. And what do we mean with first-class citizens? Now all of a sudden, event streams, we can just pass them into functions, we can get them back from functions, we can manipulate them just like we manipulate data, just like we manipulate and use higher order functions in Scala, etc. So this is really a powerful property that Rx enables for us. Then we can also view these asynchronous event streams really as collections. And just like all the other collections that we're used to, just the main difference here is just that they are asynchronous. And why and how this is the case, we'll get to that in a minute. Now, another thing that observable gives us, and that is more or less just like futures, is abstraction over asynchronous and concurrency. Right? We abstract away the details of handling asynchronous events, propagating them through to several subscribers, because observers. Sorry, I have to clarify. When I say observer and a subscriber, I often use them interchangeably. They more or less mean the same thing, especially for the purpose of this talk. But yeah, so Rx handles most of the issues that we have as developers with asynchronous computing and concurrency for us. And we will see that as well. Now, you haven't seen this yet, of course, but what it also gives us is a way to really write elegant non-blocking systems. And the thing that we should strive when using Rx is to have no blocking code at all. Our complete system should be non-blocking, right? Because that's what I think what it means to be reactive. You only do things whenever it's really necessary. Whenever items start coming in, whenever items are emitted by event streams, that's when things start to happen, right? So what we really want is to do this in an elegant way. Now, how do we do this? And this is, I think, the most important feature that Rx gives us, and that is composability, right? We can compose these observables in a very nice way, and the way we do that is by using operators. Now, operators are just, if you're used to doing Scala, you probably already know that most of these operators, but I will just mention a few of these. So this is a marble diagram. When you're working with Rx or any asynchronous programming environment, basically, marble diagrams are a good help or a good tool to reason about your event streams, about your programs. So the upper arrow represents an observable, an event stream that we use as the input, and this is an event stream that emits circles of different colors. And then we pass that into an operator called map, right? Most functional programmers probably already know map. Map takes a function that takes a circle and then transforms that into a diamond. Now, what this does is it just applies every function to every item that gets emitted, and what we get back is an observable of diamonds. Now notice that we have an observable, we apply an operator, and we get back an observable. So this allows for chaining, right? We can now chain all of a sudden all kinds of operators and operations and manipulations on asynchronous event streams. All right, let's look at another operator, filter. Another famous one takes an observable that, for instance, emits all different sorts of items. Then it takes a function, or actually a predicate, that filters out only the circles. And now we're left with an observable of circles. Right? So we could subscribe to that and only react upon circles if we would like. Then how do we compose two observables together? Well, an example of that would be the operator merge, which takes two observables as input and then basically emits all the items that get emitted by both of the input observables. Now, notice here that the X, that stands for an error has occurred. Now, in Rx, the design of Rx has chosen to fail fast, basically. Not propagate further, because the designers could have chosen to, you know what, let's just continue emitting items from the other observable. No, we just fail fast, so we can handle the error immediately and then go on with our lives without erroring streams. Now, another one, flat map, and the functional programming wizards will probably already feel the monads, right? This basically means that observable is a monad, but enough on that. Flat map basically takes a stream of events, and for each of these events, it does the mapping like map, so it takes a circle, but then returns another observable, right? So it maps this function, and then it gets for each circle an observable, and those get flattened, right? So you have, for every event emitted, a new observable, and those get flattened to one observable. Now all the items are emitted on the output observable. So that's flat map. Another interesting one is group by, which we often use in a pool setting, maybe in a SQL. Group by also takes a predicate, or I should say a selector, a key selector. So here, for instance, we can group the events that are emitted based on their shape, right? But what we get back now is an observable of observables. Right? And we can subscribe separately to these streams and handle them in the way appropriate for those specific shapes. Another one, combine latest. And I'm showing you this one because we will see it in action in a minute. This takes two observables, one that emits circles with different colors, and the other one shapes with no colors. And then it takes a combining function, which takes the latest of the first and the latest of the second, the latest item emitted, and then combines them and emits that. So this basically combines the latest emitted value from the observables into one value. Scan, and this one is interesting because you often, I see myself often using it whenever I need to, I have some type of computation that has some type of initial state, and then I have an accumulation in which I modify the state. And I do this by scan, because what scan does, it takes an initial state, and then it takes a transformation function again, which gets the accumulated state and every next item that is emitted, and then transforms it so we can basically accumulate the emitted values in whatever way we like. So what we have seen here is that there are a lot of operators, but we have operators for transforming observables, we have operators for filtering observables, combining them, we can handle concurrency, we can do error handling, and many more. And in fact, there are more than 300 operators defined on observable. So we have a wide range of, our toolbox is huge with Rx. Now, to get back to callback hell, the nice thing about these operators is that basically they encapsulate all the nastiness, all the gooey stuff of callback hell inside the implementation of these operators. So we as users don't have to worry about all the nasty things that come with asynchronous programming. That's all tucked away in these operators. And the same goes for the concurrency and error handling. That's all inside these operators, and we as users of Rx don't have to worry about it anymore. All right, now let's look at an example about how to use operators. So I will switch back to my IDE, close this file, open up operators. Let's start with a simple one. The font is still good? Anyone? Yeah? Okay, perfect. So here we have some helper methods for checking whether or not a number or a long is a prime. So what I do here, this might not be the most useful example, but it's just to show how we can create and use these operators. So I have an observable clock that is again defined in terms of this interval, and this one emits every 10 milliseconds. And then we take this clock and we filter everything that is a prime, right? So this should start emitting every 10 milliseconds a number, as we have seen, but now this new observable primes should only contain the values that are, well, primes. So now for primes, what we do on primes, we apply the operator for each. Now don't think that we went back to observables, we're still not blocking. This is just a for each, which basically more or less is like a subscribe, but meant to do side effecting stuff. So we do that, and again, we block the program, because otherwise we would just fall through, nothing blocks, right? Our code doesn't do anything initially until events start firing, so we have to somehow block it. All right, so let's run this. Run it. And what do we see? Oh, this goes quite fast, but for the quick thinkers amongst us, indeed, these are the prime numbers. So that's a simple example of using filter. Now I would like to show you another example, which is a bit more interesting, I think. Now this implements, I will first show you what it does. It's just a very simple implementation of a simple game, Snake. And when we run it, we just have this. Oh, I'm sorry. When we run it, there it is. We have the snake object that can move around, eat values, and move through walls, come back on the other side, eat again, etc. Not very exciting, but let's look at the code. You might be surprised to see that this whole this complete demo is basically managed by this one expression. Everything is done by this one expression, and then I have some three pure functions and some helpers, basically. So let's look at this expression. This expression, let's isolate it a little bit. What does it do? Well, first we again call an interval, right? So this starts emitting a pulse every 80 milliseconds. And then we call combine latest with. Remember combine latest? Takes two observables and then combines them. The latest of both observables are being combined every time that they emit, that each one of them emits. So what we do inside is I have this key events. So let me show you key events first. Key events basically exposes all the key events in this JavaFX as an observable. And how did I do that? I just called, again, this observable factory method. In Java, again, this would be observable create. and we pass it the subscriber that adds to this stage, which is the window, the event handler that takes every key pressed event and then calls this lambda and then propagates the event to the subscriber. So with this key events, right? This key events emits every key event that we hit on the keyboard. But for this demo, we're only interested in arrow keys, so we filter that guy on arrow keys. So now what are we doing really? We're combining with the key events with the interval, and this is actually a combine latest with, which actually does a map afterwards. So after the combination, it calls the function getDirection, and it basically gets the direction of the key that was pressed. So this, actually, to make it a bit simple, you can do it like map and then do a normal combine latest. This should do the same. Oh, no. Okay. Oh, sorry, let's see. Oh, well, I know. This should be, because now it emits tuples. What? Anyway, the function combine latest with basically maps the getDirection function after the items get combined. So afterwards, what we do is we call the scan operator. So scan just takes an initial state, like we said, and then the accumulated state S, and then the direction that was basically emitted from this function. So this direction, every time we get a tuple for this scan, and what we do is we apply 3 pure functions. So first we do a move snake, then we handle the collision, then we eat the candy. So move snake basically takes a state, returns a state, and the same goes for handle collision and eat candy. Now, this next operator is an observe on, and we will talk about this one later. But what it does is it switches our operation to the UI thread, right? Because if you're updating the UI in JavaFX and in many other UI settings, you cannot update the UI from another thread other than the UI thread, basically. So that would result in an exception. So what this does is it switches the operation to the UI thread, and now we can call draw scene for each of the emitted items. And this is it. This one expression basically manages the whole game right now. It's one chained expression of observable operators. All right. Let's continue. Okay, now let's talk about a very important distinction between the types of observables, the types of event sources that exist. Now this distinction is not one that is present in code, it's just a distinction that we as developers just must be aware of, right? The way that we handle these our observables is really dependent on this one distinction. So this distinction is basically the notion between hot observables and cold observables. Now, let me start with cold observables. Cold observables are observables that basically emit items separately for each subscriber, right? So if we look at this example, this starts an observable of interval, which again starts ticking, emitting time ticks, and then we subscribe twice, right? Now, if we would wait before the second subscription, right? We subscribe to with the first observer, and that prints every item. If we would wait until we subscribe for this with the second time, what we would see is that the second one would restart the ticks, right? So ticks go 1, 2, 3, 4 for the first observer. Now the second one would just restart these ticks. It would basically have its own source of these events, right? And we will see this in action in a minute. Now, for a hot observable, that really isn't a possibility, right? If you think about your mouse as a source of events, you can't really have a different source of mouse events, right? There is one mouse, and you don't really have a choice on what you're observing. And moreover, you don't even have a choice of when this observable starts emitting these events, right? Because the user is just, moving his mouse, he's pressing buttons on it, and that thing is just emitting events, whether you like it or not. It doesn't care whether something is subscribed to it. So that is basically the notion of a hot observable. So if we think about it, a hot observable really fires events independent of whether or not something is subscribed to it. Whereas a cold observable really waits until something is subscribed and then it starts firing events, right? So for hot, think a mouse, and for cold, think something like an array or cold storage, a database, maybe a hard disk, whatever. Now, here in hot observables, basically the same source of events is shared by all the subscribers. And for cold observables, like I said, every subscriber has its own private source of these events, and that's why it can, when another one subscribes to this cold observable, it can get its own stream that has, for instance, begun from the beginning. Now, the real difference, the essence of this distinction is that whenever you subscribe to a hot observable, there is no side effect, right? Because the thing is already emitting. The events are already flying, so there is no side effect due to this subscribing of an observer. Whereas when you subscribe to a cold observable, actually there is a side effect, right? Because that's when the observable starts emitting items. So let's look at an example of these hot and cold items. All right, let's close these. Hot and cold. So let's first look at a very simple example of a cold observable. So what this does is, again, emits time ticks. Like I said, we subscribe once with a function that just prints every item. Then we wait for a read line, so I must press enter, and then the second subscription happens, right? And we block for the program not to terminate prematurely. Now let's run this. Increase the terminal. Okay, so the first observer is subscribed, and we see that it's emitting, the observable is emitting these items. The second one is not subscribed yet. So now if I press enter, what we see is that the second one is also subscribed, but it has restarted basically from zero. Right? So here we really see this effect of having this cold observable, this cold source of events that just can restart whenever a subscriber subscribes to it. Okay. Now let's contrast that with a hot observable. And this is a bit more of an involved example because I wanted to show you the mouse moves. Now mouse moves, again, just like we wrapped the key events in the snake example. Here we wrap mouse events basically the same way. We just add the event handler to the canvas and then on next every event that gets emitted. Then we subscribe immediately with one subscriber, start printing everything. And then we have, this is a small mechanism that I coded to have the second subscription a bit later. So what this does is basically waits for 5 seconds, does nothing. Then this is not really used. This will basically emit every 1 second a new time tick, but because I'm getting the head, which means taking the first element that gets emitted afterwards, that stream basically stops. But what I do is flat map that one event that gets emitted out of this head with mouse moves. So these mouse moves are now basically continuing the stream. and then we subscribe to these mouse moves. So all this really does is just wait for 5 seconds and then subscribe to mouse moves and start printing. All right, so when I run this, all right, so when I move my mouse right now, I see that the first observable was emitting items, and then after some time, the second observer started to print. So, but what we see here is that they immediately got the same event. They started at the same point in time. They were sharing the same source of events, and the things didn't restart. Well, that's obvious because we're talking about mouse events here. But that is really in contrast to what happened with the cold observable, right? So cold observables restarted the event, and hot observables, basically when you subscribe, you just jump in and start catching the events that are being emitted at that moment. So is this distinction clear? Are there any questions about this?
I have a question.
Yeah?
I'm wondering if you could give a more real-life use case for cold observables?
Sure. Well, like I said, you can... Sorry?
The question, please.
Yeah, so the question is if I can have more real-life use cases for cold observables. Well, imagine if you have a list of items, or let's say you have some data in a database or on a hard disk, right? That data is just there, waiting to be pulled out, right? And then we can wrap that in an observable and start reacting to everything that gets emitted. Now, what you can do is, obviously, just re-emit from the beginning every time that a subscriber or an observer subscribes, right? You're not limited by the fact that these events happen more or less in real time. You can just create this every observer can have its own source of these events. Right? Does that more or less answer your question?
Well, I see that it's possible to have the cold observer, but I don't yet see why you would want it, but maybe I should ask that.
Well, think of this, getting something from the hard disk takes a long time, right? And I might be, maybe I want to read 10,000 files. Right? Am I going to wait for every of these files? Am I going to block my program before that operation is done? No. What I do is I wrap these events in an observable, right? And then if I am interested in handling them in 2 different ways, right, I could subscribe twice and have one observer having its own source of these file events, and then another observer having its own source as well. So they're not affected. They don't have this limitation of having the same events. All right. Any more questions? Okay. So that's hot and cold. Now let's look at how to create our own operators. Like I said, there are a lot of operators in Rx, more than 300, and there might be a use case in which we see this pattern that we keep using for these observables, and maybe we want to create our own operator to. Yes.
Maybe there is an operator for this little thing you were doing with these 5 seconds and then a second.
Could be.
That's relatively low level. Maybe there should be an operator for it.
Yes, could be. I don't know. I haven't memorized all the operators, to be honest, but it might very well be. If not, we have all the tools that we need to implement them ourselves. So one option is if we want to create our own operator, is basically in Scala we can do a very nice thing with extension methods, and just extend the observable object and use existing operators, combine them to create our own new operator. But that only goes as far, because maybe we want to do something really exotic, and we need to do some administration or whatever. So that takes us to some points, but a more general approach would be to just use the observable create. So in Scala, the observable apply factory method. And in that case, and I will show you how that works, we just use that mechanism to create a new observable given some other observables and some other things. And then the third method is the method that RxJava uses internally to implement the operators, and that's basically lift. And we will talk about that in a minute. Let's look at how we would like. Let's say we want to implement this map and filter operator, right? Very simple. It just maps a function f on the stream and then applies a predicate to filter out some values. So first we have a function on an observable of t. We have a function that goes from t to r, and then we have a predicate that takes an r, returns a boolean to see if it should be filtered or not. Now, obviously, this is not implemented on the on observable, so we have to do it ourselves. Let's see how we can do that. Let's close these. Okay, so the first, and since this is really a simple combination of operators that are already defined, the simplest and most pragmatic way would be to just use the map and the filter. So what I'm doing here is I have an implicit class, and for the non-Scala people, with this implicit class, I can define extension methods that on an other already existing class. So I can extend some class that is already existing with some extra methods. So what I'm saying here is I have a this observable class, and we just call the this pointer, we call that obs, and that we can extend with these functions. So this is map and filter 1, that, as we said, takes this function to transform and then the predicate, and then returns an observable of type R. Well, all we do is take the observable, map the function over it, and then call filter. Well, easy as that. But like I said, maybe this is really a use case where this is simple and possible. But it might be the case that this is not, that we want to do something more involved. So how would we go about that? Well, then we would use the factory method, so observable create or observable apply. And what we do here is we are given, so we have this input observable obs. We have the functions and the predicate, obviously, and what we need to do is create this new observable of R. Well, let's do that just by simply calling the factory method, observable of R, that gets a subscriber. But now what we do is we subscribe to the this pointer, basically. So the first input observable, obs, and we subscribe it with 3 lambdas. This is the onNext, this is the onError, and this is the onCompleted. So the onNext, what it does is it subscribes to the original stream that we want to map and filter over, and then for each item that we emit, we apply the function that we're given to that item. Then we get the transformed item, x in this case. Then we check whether or not the predicate holds for that transformed item, and then we basically propagate that through, in that case, to the subscriber. If anything goes wrong, we send an onError event. Sorry, yes?
Quick question. So for the Java version, since we don't have implicit
Yeah.
classes, how would you get the original observer instance?
Yes, so in Java we don't have this nice feature indeed, and we cannot use extension methods to create our own operators on observable itself. But what we can do is just, for instance, create, let's say, a static method that takes an observable, another observable, whatever it needs, like a function, a predicate, and then returns another observable. Right? So it wouldn't be as elegant as this implicit extension method, but it's very much possible. Right? Does that answer your question? Okay. So, but and the other solution would just be to switch to Scala. Okay. So now notice one thing, that actually this implementation isn't all that great, because anything can go wrong in this function, right? The function that gets passed in to transform the item. Anything can go wrong there, and also anything can go wrong in this predicate. So what we had to do actually is just wrap this in a try block as well. And if anything happens, we just catch the error. We don't really care what it is, so indeed, I'm catching throwable. And then ops on error here. Sorry, of course not. Subscriber dot on error. This, right? So this would be a more safer way. Okay, so if anything goes wrong, the error callback is invoked on the subscribers. So this shows us the two more or less simpler ways of creating our own operators. But now let's think about how to use Now let's think about how to use the lift method, right? So a little bit of history about this lift. So like I said, the initial implementation of Rx was for the .NET platform, and there they didn't have this lift method yet. It still doesn't have the lift actually. The lift method basically, so from RxJava 0.17 or 0.18, they switched to this lift-based implementation. And that really took a lot of basically code repetition inside the library was vanishing due to this lift, and also the speed suddenly became a lot better. So the performance went up. But now let's look at what this lift really is. Now in theory, how we would think about lift is that it is a function that takes a function from observer of R to observer of T, and then returns a function from observable of T to an observable of R. Right? Now in these type variables, you already see a bit of the contravariance of this lift method. So the interesting thing is that we just take a transformer of observers, lift that to the level of observables, and all of a sudden we get an operator. So now this is how we would define this in theory or in Haskell. In reality, we're in an object-oriented setting. So what we do is we take the first observable that was from the resulting function and make that the dis pointer. Right? We operate on this on some instance observable of T. We give it a function. We lift a function from observer to observer, and we get back a new observable. So let's look at an example. And actually, I think the type of this lift is very interesting, because if you let me pull out the code. If you really think about it. And stare at this type long enough, maybe with some beer or some whiskey, what you will notice is that there is actually just one possible implementation for this function. And it's really simple. It's really simple. And this might be a bit magic, but trust me, there is no magic at all. It's really... So what happens here? I have, again, an implicit extension method on observable of T, and I have this myLift, which is my own implementation of this lift method. So this takes an operator that is a function that takes a subscriber, or observer of R, and then returns a subscriber of T, right? And in the end, after lifting that function or the operator, we get back an observable of R, so the transformed observable. And what we do here, the only thing that we really can do here is create this new observable, and this is actually an observable of R, right? Because that's the result type. And we're not thinking here, right? We're just following the types. And we pass in a function that takes a subscriber, so that is the subscriber of R, and now we need to somehow get a subscriber of T. Well, what do we have? We have this observable of T, to which we can subscribe, but now we need a subscriber of T, right, to subscribe to that observable. So how do we get that? Well, actually we have a function, an operator, that takes a subscriber of R, which is this guy, and then transforms it to a subscriber of T. So there you have it. All the types line out. We don't even need to run this code. We know if it type checks, it works. Of course, I'm joking, but this is the actual implementation, and you will see this is the only sensible implementation of lift that you can do. Now, using this lift, let me increase this. We can implement this map and filter in this way. So what we do is we lift, oh sorry, this is the normal lift. I can just replace this by my own lift, my lift. And map and filter is now implemented just by passing in this function that takes a subscriber of R, creates this new subscriber of T, and I'm not saying this is nicer than just combining existing operators, but as I said, that cannot always be done. So again, here we do the same basically. Apply the function to transform the value, check the predicate, and then annex the event. So the thing is here that you gain a lot in terms of efficiency for implementing the operator in this way. So if we look at other operators, for instance, we can implement map, and map is actually quite simple. You lift a function that creates this new subscriber, and all we do is, we propagate the errors, we propagate the completed, but before we propagate the next event, we just call f, which is the transforming function, and now we have, created this our own map. Same goes for filter. We just check the predicate, annex the event, and otherwise we don't do anything. So, and this way we can implement basically a lot of operators here. I have tail and flat map, but I won't go into the details of these. Oh, sorry. Yeah, oh, sorry.
So what I got out of that is
Yeah?
that essentially it's a nice way to get rid of this try-catch business you were doing in the previous implementation.
No, actually, that is not the essence here. You still need to check for that try-catch. So things can still go wrong. The idea here is that you get a lot in terms of efficiency, right? Because like I said, when RxJava switched this implementation from this manual code repetition everywhere to this lift-based implementation, everything went a lot faster because everything is optimized for this lift, right? This lift method is optimized, and that's what you really gain. Now you don't have to use it, but if you have some operator, if you have some pattern that you see yourself using a lot, and maybe it's a bottleneck, then you just implement it in this way and gain some performance.
Do you know why it's faster? Is that the compiler?
Yes, so that's the interesting thing. In Rx.net, they did a lot of manual optimizations. So they manually optimized a lot of code. If you look at the source code for Rx.net, you see that it's really complicated just to get a lot of performance wins with these things. But with Lift, what happened is that the hotspot was able to optimize this code for you. So you didn't have to do these manual optimizations anymore. You just had the hotspot and the JIT basically optimize the code for you. So that was the reason. Does that answer your question? Yeah? Any more questions? All right. Yeah, sorry.
For instance, with the lift, if we read in a file, we can have an observable of lines, strings, and
Yes.
turn this into an observable of JSON line in a certain type, for instance.
Yes.
Given the transformation that go from string to JSON, kind of thing.
More or less, yes, indeed. That's what we're after. We want to transform or manipulate or filter or do some type of operation on some input observable and then get a new observable. So indeed, transforming an observable of string to an observable of, I don't know, JSON objects is indeed what you could accomplish with this, with lift. But you would only use lift if you want to have your own operator. So usually transformations, the operator for that, for transformations, are already implemented. So you don't have to go and implement all that yourself. Right? Okay. More questions? Okay. So I think it's a nice time to have a break. And then when we get back, we will dive into the foundations of Rx. Right. Welcome back, everyone. We left our journey into Rx before the break exactly at the point where we were about to dive into the rabbit hole in the theory that is behind Rx. So don't worry, we won't go too deep inside the rabbit hole, but just deep enough to understand the essence and where observables really come from. So let's start looking at the iterable type. Like we said, an iterable is a class that has a method iterator, right? And that is just a function. We call it without any arguments, and we get back a iterator of type t. So in essence, we can represent that with a function that takes nothing, an empty tuple or unit, and returns an iterator of type t. Now, what is this iterator of type t then? That is just something that we can call the next method on to pull out in a blocking synchronous manner events one by one. So how would we model that method? Just by another function, so that's the blue lambda on the inside, a function that we call again with no arguments, and we get an object of type t. Now, in reality, of course, the real life is not as pretty as theory. Things can go wrong, and things can also finish. So instead of returning something of type t, now what we do is we return something of try of option of t. Now, that means that the try says that the computation can fail, or it can succeed, so it can result in an exception. And the option says that either we have this value t, or we have it's done. So there's nothing, meaning the iterator is finished. So this is the type, right? The outer type is getting the iterator, right? Calling iterator, and the inner function is just the next method that embodies also the fact that things can go wrong and complete. So, like I said, outer is getting the iterator, and the inner is actually pulling the function to pull out one by one the values, right? So, if we just look at this type and focus on the arrows, and don't blink because you might miss it, but what we're going to do is apply a mathematical concept called dualization, and that is a fancy word for saying I'm going to invert the arrows. And then we have this. Now let's write that from left to right so that the arrows are in the proper direction again. And what we see here is that we have magically arrived at the observable type, right? We have a function that gets a callback, which can either take something that goes wrong, of actual value, or or a completion event, and then do something. So let's look at this type. If we characterize this, the blue lambda, that represents the observer, right? The observer that we have seen before. Try can go wrong, option can emit the value, or it can emit nothing, meaning that it has completed. And the outer lambda is the subscribe method. So in Scala, what we would do is take this try of option of t and then pattern match on it. So success of sum of t and then do something, or success of nothing, meaning we have completed, our failure with some error. But honestly, this I find this a bit nasty. So, pattern matching doesn't really cut it for me. What I prefer is to just pass in 3 lambdas, just the on next, the on error, the on completed, and that basically represents this one function try that takes a try of option of t and then does something without returning anything. And the outer lambda again, that is the subscribe method. So what have we done here? We took the iterable, we have looked at its type, boiled down to the essence. We have we did the same for iterator. Then we had one type, dualized the whole thing, basically inverted the arrows, and now we have arrived at the observable. So that is basically how observables came to be. And now is actually a good time to talk about the Rx contract. So the Rx contract is basically the law in Rx world. And this first line says that it's basically a regular expression of the behavior. So it says that we can have 0 or infinitely many on-next events, followed by an optional, uncompleted, or an on-error. So that means that after a completion or an error event, we cannot get any more on-next events. Those will not be propagated through to the observers. Now, one thing that this regular expression doesn't tell us is the fact that all these on-next calls happen sequentially. So the Rx contract basically guarantees us that no overlap on-next the events will not come in an overlapping way. They will all happen sequentially on if they're on a single thread. Now, a word of warning, and I had this question also during the break, and I must advise you to never implement observables or observer yourself. Just use the factory method to get all the magic and all the internal functionalities and create your observables in that way. Because if you if you do implement them yourselves, now you have to make sure that your observable abides by this contract. So, and that is not easy, I must say. So if we look at an example here, we create this observable of string, right? Again, we pass in an onSubscribe function that takes a subscriber and then does some stuff. First it calls onNext on the subscriber, then it completes. So now by the contract, nothing can propagate through anymore to the observer. And even if we call subscriber onNext and subscriber .onError, those will not be propagated through to the observer. So those calls are just there for nothing. Yeah, that's how we enforce the Rx contracts. So let's get back to the essential type of the observable. And the real functional programming ninjas probably already see that actually observable is in fact an instance or a subtype of the continuation monad. So I won't go too deep into that. That's enough rabbit hole for today. We had our fair bit of science, but we have seen how we can derive these observables in a very elegant way. Now let's look at some real world things.
Question?
Yeah.
What was
Yeah.
ULA standing for?
EULA. That's end users license agreement. It's just the contract. Yes, more questions on the derivation contract? All right. So a real world example. One of actually the school book examples of reactive programming and reactive systems is basically Excel. So in Excel, I guess we all know that you can enter values and formulas, and whenever values change, those values get propagated through automatically, right? So Excel is in its essence really a reactive program. So if we look at this small worksheet of an Excel file, what we see here that every cell, say the upper cells, they have a value. So what how would we represent that? As an observable, right? These cells can send out items or values to other cells. Now the bottom cells show us that actually cells can also receive values from other cells and propagate that through to again other cells. So what do we learn from this? Actually every cell in Excel is an observable as well as an observer, right? So back to the small visualization we had of Rx, and time to add the next concept, and that is a subject. So, like I said, a subject is something that is an observable and also an observer. So, if we look at this, it can basically do both the actions on the arrows. It can subscribe to other observables, and it can also emit items of its own to its subscribers. So, yes, it's an observable and an observer. And was there a question? Oh, sorry. We use subjects more or less like a bridge or a proxy when we want to expose some type of, say, expensive event source, or we want to bridge some type of, usually we use them at the boundaries of our system, where we go out of our internal system and make calls to external systems. So one of the use cases for subjects is when we want to share an event stream. So what we have, let's say we have some observable, and subscribing to that might be really expensive or complicated, or for whatever reason, we only want one subscription on that source, but then we want to have several other subscribers to subscribe to that basically proxy or that bridge, right? So what we do is the subject subscribes to the source, and then the other observers subscribe to the subject, and that way the event stream, the source is shared over the observers. Now, what that also means is that if that source is a cold observable, now all of a sudden it becomes a hot observable. So, and that is because it was cold, it was waiting until someone would subscribe to it, and now all of a sudden the subject has done the subscription, and the others subscribe to this subject. So the subject subscribes, the event source starts emitting, and whoever is subscribed to the subject will start receiving the events from the source. And they will share the same events and the same source, basically. So like I said, the typical use cases are at the boundaries of your system, where your system goes out of the elegant composition of these event streams into the real world or external systems. But there are also other legitimate use cases like Excel, for example. But I must say, you must really try to avoid subjects as much as possible. So you see that a lot of beginning Rx programmers really embrace these subjects because they make things a bit more easy and processable in our old-fashioned way of thinking. But in 9 out of 10 cases, you really don't need subjects, where you can just suffice with having the observable create method, for example, and wrap your events inside that. But nevertheless, there are legitimate use cases for subjects, and I will just show you the 4 important subjects that we have defined in Rx. One is the async subject. So this subject subscribes to a stream, and it doesn't emit any of the items that the stream is emitting, but only once that input stream has completed, it will emit the last item. So you can imagine, for instance, that you have a stream of, say, I don't know, stock options, and for some reason you're only interested in the option at the end of the day, right? Then you could use an async subject. And you see, it doesn't matter when subscribers subscribe to the stream, they will get the same value at the same time when the stream completes. Now, another subject is the behavior subject. Behavior subject takes an initial item that it starts with, and then once a subscriber subscribes to the subject, it emits immediately the latest event from the source stream, right? So what we see here is that the first observer subscribes when there are no streams emitted yet, so it will get the initial item, and the second subscriber gets the latest value at the moment of subscription. And from that moment on, they both get the same items that are emitted. Then we have the publish subject, and that one basically does the same, more or less, but without the initial without emitting the initial value or the latest value. So here, what you do with publish is exactly what we said with sharing the event stream, right? You have this one observable that emits items, and whenever the first subscribes, he just receives those items, and then a second observer jumps in, and he starts from that item on, receiving those. And then we have the replay subject, and that is one that basically buffers, or basically remembers all the items that were emitted on the stream, and whenever a subscriber subscribes, it replays all those items emitted. So for the second observer, we see that it subscribes after the second event, but it immediately on subscription receives these two events when on the moment of subscription. So now a question for you maybe is, which one of these subjects would model an Excel cell? Which one would we use? Anyone? Ah, yes, behavior. Because what you want is for whenever you use a formula that is dependent on a value in another cell, you actually want to get the latest value from that cell, to use that and compute the current result. You don't want to wait for the cell that you're subscribing to actually emit a new item. It has already emitted, so you use the behavior subject to get the latest value and compute the result. So indeed, behavior subjects model the cells in Excel. So let's look at an example in code of subjects. Yes?
Can you go back to the async one?
Yes.
So suppose the async itself emits only one thing.
Yes.
So is it then my intuition right that the subject is for the observable a little bit like a promise is for a future?
Yeah, not really. Maybe in the async subject case. So
Well, in the async subject.
yeah, sure.
It says that it does its thing only once, but many people can basically, between quotes, subscribe to the promise.
Yes, but
Here's a question from the back.
yes.
No, repeat the question.
Oh, sorry. So the question is whether or not this the behavior of this async subject resembles what a promise is to a future. Now, what this does is basically drop all, not propagate all the other events further, right? So that's a difference there. And when it completes, so it's not waiting for a value to complete and propagate that. It actually waits for the completion event of the whole stream, and then it emits the latest value.
Yeah, but I was saying assuming there is only one.
Oh, sure. Okay. Then there is indeed a resemblance.
But it is an argument of the subject or of the subscription for the period. Can you have the last stock every day for one subscriber and one stock for every week for another subscriber?
Well, yeah, you could do that. You could. What you could do is, because the stream ends, right? Once the completion event is emitted, no more events will be emitted, like we have seen for in the Rx contract, right? But what you could do is, on completed, resubscribe to the stream for the next day. Yeah, does that answer your question? Any more questions? Yes?
Why should we avoid using subjects?
So why should we avoid using subjects? Because when you use subjects, not in all cases, but in 9 out of 10 cases, it means that you're depending on some type of mutable state, right? Because subjects give you the power to subscribe to events on the one hand, and also re-emit items on behalf of those on the other hand. You're both an observable and an observer. So you can see that more or less like having mutable state. And I think the consensus amongst programmers is more or less that mutable state is something to avoid if possible. Does that answer your question? Okay. Any more? Okay, then let's look at some code that actually uses subjects. Sorry. Here we are. Okay, let's look at this replay subject. Well, what we see here is we create, we create this a replay subject of integers, and then we immediately subscribe this one subscriber that prints every item, and then we on next 3 integers, and afterwards again we subscribe another subscriber. So if we run this, what we expect to see is that although the first subscriber has subscribed before all the items were emitted, so he gets all the items immediately at the moment of emission, but this guy, the second subscriber subscribes after the events are submitted, but still he has emitted all the items. Hello. Yes, there we are. Where was I? So yeah, so the second subscriber has subscribed after all the items were emitted, and but still has received all of them. So this is the effect of the replay subject, and you really see here that on the replay you can call the on next method. So from wherever you can just start emitting items, right? And also you can just you can pass in, if you have, let's say, another observable, let's just say never, then I can subscribe with this replay as well. So that's why it has 2 characters, and it can mutate basically the event stream, and that's why they should be avoided if possible. All right, so that's the replay subject. Let's look at.
Could you subscribe to the replay subject?
Yes?
Even after an error has been.
No. The subjects also abide by the Rx contract. So you can subscribe, but you won't get any items. I mean, you can call subscribe, but the source has already. Well, actually, I'm not sure if I'm. Let's try it out. Replay. Let's see what happens. Okay, so indeed, the replay subject just replays the complete stream. I was wrong, I'm sorry. Even after subscribing after a completed event, you still get the complete stream. Yes?
So for the fun of it, if replay observes replay?
Sorry?
If replay observes replay.
All right. Let's try that. Subscribe replay. Now, this will basically propagate its own events through to itself. But fortunately, well, the complete doesn't really matter here, because what it, okay. It doesn't really do anything with the events, right? It just gets them back itself. And what we see here is, it just goes round and round. It just, every item it emits itself, it gets back itself. So, I'm not sure if this really is a legitimate use case, but you see that you can do some funky stuff with these subscribers. And, beginning to program with Rx, you are really inclined to use these things because, they make life a bit easier before you really get the idea of programming with Rx. But really try to avoid them as much as possible. Sorry?
Do an implementation of the game of life?
I guess that would be possible, yes. All right. So, okay, let's look at the publish subject. Here, this is a more involved example. So here we create a publish subject of integer, and recall that publish subject basically just makes sure that all the subscribers share the same source stream. It doesn't do any buffering or emitting earlier items. Just make sure that the subscribers share all the events. So here we on next first to this pipe. But since there are no subscribers yet, nothing happens. It just basically disappears into void. Now here we subscribe the first subscriber. Right? We have the 3 lambdas. On next we print it. We print the error if something goes wrong, and on complete we print done. And now if we on next, this subscriber, since he is subscribed, he will get this value 1. Afterwards, we subscribe another subscriber with basically the same lambdas, and then on next another value. And now both A and B will emit the second item. Now we unsubscribe the first subscriber, emit another item, emit a completion event, and then emit another item. Right? So this item will go to only the second subscriber, then this will complete the stream, so the second subscriber also completes, and this one, according to the contract, will go into void. And the third subscriber, this guy is basically subscribing at the moment that the stream is already completed. So indeed, in this case, not with the replay subject, but in this case, it will fire the completion immediately. And again, this on next will throw its emission into the garbage can. So if you quickly run this, we see that indeed everything is emitted up until the point that the stream completed, and everything else has been discarded. And also, the 0th value that we emitted before anyone was subscribed also got discarded. Okay, so are there any... Yes?
What was the rationale for the very last line, so that the C still sees the completed? It might actually maybe not even see the completed.
Sorry, you mean this?
C here, so the last line, C sees the
Yeah. Yeah, so...
What was the reason for that?
Well, because C subscribes at the moment that the stream is already completed.
Yeah, but it might not even see that one. It might not even see the done.
Yeah, that would be an option, but in this case what Rx does is it fires the uncompleted event immediately, so that the observer knows that, well, you know what, you did subscribe to this stream, but nothing is going to happen, so you try something else. Or yes, more questions? All right. So those were subjects, and again, I want to really stress that you avoid them as much as possible. All right. Now let's talk about distributed systems and concurrency. So the combination time and distributed systems is really a complicated one. So what Rx does is basically duck the question and just virtualize time. Okay, and it does this by adding another component. So if we look again to our small visualization of Rx, then we add the next component, and that is the schedulers. So schedulers are basically these objects that give us control over concurrency. Right? We can really manage concurrency of these event streams really in an elegant way. Now, this might surprise you or not, but Rx is really single-threaded by default. And actually, that's a good thing, because one of the things that I haven't mentioned is that Rx really has no opinions as to how to do things. Right? Rx doesn't say you have to manage your events in this way or in another way. Rx really gives you the tools to elegantly manage your event streams, but it doesn't force some type of opinion on you. So by default, it's single-threaded, but you can use schedulers to allow to introduce concurrency. And to introduce concurrency, we can use these two operators. One is observe on, and the other one is subscribe on. And what they do is they just operate on an observable and take some scheduler, and they basically that will have the effect that it switches its operation to another scheduler or thread. So in the case of observe on, you give it a scheduler, and then it will do all the observe callbacks, so all the lambdas that are for the observing of items. Those will happen on another scheduler. Right? They can happen on another thread, they can happen on whatever, but they won't happen on the same thread as the emitting observable. And with subscribe on, and you have to be careful with this, with subscribe on what happens is that you give it a scheduler for the onSubscribe function to run on. Right? So the lambda that we pass in to the factory method observable create or observable apply in Scala, that function, that method will run on another scheduler if you use subscribe on. All right? So another thing you can do with schedulers is use them to schedule your own work on subscriptions. And we will see that in a minute. And one of the really interesting and powerful things about these schedulers is that they really give you the power to become a master of time. Because like I said, Rx virtualizes time. And with the test scheduler, you can control the time basically of the operation of an observable. And I will show a demo of that as well. There are a lot of schedulers, but I will discuss the four most important ones. So first is the new thread scheduler, and the new thread scheduler basically creates a new thread for each unit of work. Right? So you can switch to another thread and continue the handling of emitted events on that thread. With the I/O scheduler, you can also switch to another thread, but this scheduler is really meant to be used if you have some type of operation that does a lot of blocking I/O. So if you're doing some type of I/O that really is blocking, use the I/O scheduler. And if you have some type of computational work that does any type of work that doesn't involve blocking I/O, for that you can use the computation scheduler. And the final important one that I want to talk about is this test scheduler. And with this scheduler, like I said, we really control the flow of time, and with that, the emission of events on our observables. And so we can use this, for example, to test things. So we could write unit tests on asynchronous event streams, and advance time by, that's an actual method on this test scheduler, advance time by say 3 seconds, and then see what has been emitted and check whether or not that is what we have been expecting. But there are also other use cases for the test scheduler, and I will show one of those. So now the elephant in the room, parallelism. How do we use schedulers for parallelism? Well, actually, it's quite simple. And a word of notice, there used to be a parallel operator in Rx, but that has been deprecated and maybe even removed because the parallel operator didn't really do what people expected it to do. So to parallelize some operation on every event that gets emitted on a observable stream, you can use this pattern. So say you want to do this stuff with item in parallel for every item that is being emitted. What you do is you just flat map a function that takes that item, then runs that do stuff with item, but this do stuff with item must return an observable, right? So you do your operation and inside this observable stream, and then you subscribe on some scheduler, right? So now for every item that gets emitted by the source observable, you basically switch to another scheduler, so every item will be handled on its own scheduler, on its own thread, and things will just happen in parallel with this pattern. So let's look at an example of this, how this actually looks in code. Schedulers, parallelism, right. So here it is. Let's say I have this source observable that basically is observable from a range of 1 to 100. So this emits, well, obviously 1 to 100. And since this is not on a scheduler, this will just happen sequentially. But now on this source, we apply this flat map that takes the event, calls this do something, and then subscribes on another scheduler. So let's see what do something then does. Well, do something takes the emitted item and then creates a new observable and then does something. So this can be some computation, some network call, something with high latency, can be anything. For now, I'm just making the thread sleep for a random amount of time, just to simulate that effect of latency. And then we emit the resulting item, but actually we transform it to a string so that I can print the thread ID together with that emitted item. And once that one item is done, we just complete the stream, and that's it. So if we run this, what we see, run parallelism, is that all these items, which would have they would have normally, without this subscribe on this I/O scheduler, they would have happened in sequence. Now you see they're all scrambled up because we were waiting for some random amount, or sleeping for some random amount of time. And also we see that they all happen on their own thread, right? So we have successfully parallelized this stream. Now, if we would remove this subscribe on, then restart this. What we then see is that things just happen the way we would expect things to happen on a single thread. And there we see the same thread ID. So this is how you parallelize things using Rx. Now another, yeah, sorry?
Can you do the other way around? You have a number of observables and pipe through them for a single thread?
Yes, yes. So you can also create your own schedulers that, for instance, what you often do is you have a lot of observables. So you have one observable handling mouse events, another observable handling some key events, another observable, getting some data from a network. But at the end, you just want to show everything on one UI, right? So what you do is, once all the values are done, you just, switch to the UI thread. That is just one thread. You have to switch to it, otherwise nothing gets rendered. And, things get rendered on that one thread. So that is a common pattern for mostly UI work. Yeah? More questions on this? All right. Okay. Now let's look at another thing, a stock parser. And here I want to show you the power of the test scheduler. Now this isn't the most involved demo, but it really shows what you can do with this notion of virtual time. Right. So what this does is I have a simple case class of stocks. Not interesting what these are all economic values that we don't really care about, but we have to create this observable of stock. And we do that by just scanning a file, a JSON file that contains lines of stock, basically. And what we do here is we have this test scheduler on which we create a worker. So this is what I meant with scheduling your own work. And what we can do with this worker is just schedule some action, for example, periodically, right? So we say, you know what, wait, initial delay is 0 minutes, so don't wait for this work to start. Then we do this work and then redo it every minute, right? So what we do here is we just check whether or not we still have a next line in the stock input. We parse that line and then emit, so this parse returns a stock, and then we emit this one stock. So, and if we don't have a line, obviously we complete. If something goes wrong, we propagate the error. Now, the interesting thing is, so this whole definition, obviously, of stocks is non-blocking, right? This is just, this will fall through. Then we subscribe to the stocks with a simple single lambda print line. So for the non-Scala people, do I see a question? No. For the non-Scala people, this is just a function that takes an event and then prints that. So this is that was just syntactic sugar for this, basically. And what we get back is this subscription, as usual. So now that we're subscribed and able to print these things, we have this, for the purpose of this demo, this blocking while loop, that while the subscription is still subscribed, so not unsubscribed, what we do is we wait for a read line from the user, and then we advance the time by 3 minutes, because we know that we get a stock every minute, so it was not arbitrary that we scheduled every emittance of a single stock for a minute in virtual time. And now what we do with every press on the enter button, we advance the time by 3 minutes, right? So now, if we run this, what we see is that every time we hit enter, we get the next 3 minutes worth of stock. So here you really see the virtualization of time in action and how you can manipulate time. And obviously you can use this for things like this to play around with these, with virtual time, or you can also use this for testing, obviously for, writing unit tests. Advancing time, checking if things are emitted that you were expecting to, and then advancing the time some more. So, are there some questions about this? Yes?
Create worker, can it be done with every scheduler?
Yes. Every scheduler has this create worker, and we use these workers to schedule some work. And if you look on this, so we have just a single schedule, so that this just is a one-shot action, right? We just schedule a single action. Then one with a delay, and then a single action, and this is the one we use. This is periodic scheduling, and then we have this schedule recursive method, which basically does the action and then recursively calls itself. And the reason why we don't just simply have a loop inside this scheduler, but actually recall ourselves recursively, is to have a moment in time in which subscribers can actually unsubscribe. Otherwise, unsubscribing would be probably impossible. Any more questions on schedulers? All All right. So back to the slides. All right. So that was schedulers. Now we have to talk about a not so pleasant topic. Oh, sorry. Oh. What happens when, I'm sorry for this, what happens when a producing, so an observable is really, producing very quickly and the consumer can simply not keep up, right? It's just, hitting the consumer with these events or items and, the consumer can just simply not handle it, right? This is a situation which, in this situation, what we want to do is apply back pressure. We want to slow down this observable. Now let's look at a concrete example in Rx. So as we said, observe on is used for schedulers, right? So you have an observable stream of events, and then you use the observe on operator, give it a scheduler, and that will basically switch the operation of these events to another thread, for instance, right? Now, let's think about this. What does observe on really do in reality? So, observe on is just this operator that gets items from one observable that is operating on its own thread, say thread 1, and then basically outputs those to another thread, to another observable which is operating on thread 2. Now, internally, obviously, observe on must have some type of buffer, right? Because the left observable is putting items in this buffer, and the right one is taking them out. Now, if this first observable is really fast, it can obviously drain the buffers, right? And the consuming observable is not able to keep up, well, then you have a problem because buffers are not infinite. So what we really want to do is apply back pressure. And that just means that, well, like I said, it's a situation in which the observable produces much faster than the observer can consume. And this is actually a problem that I personally think is really hard to solve. And I don't have a formal proof on this, but I think in the general case, it's actually impossible to solve. Because if you really think about it, asking an observable to slow down is basically the dual question of asking an iterable to go faster, right? I mean, an iterable, you can optimize the operations that you do in this blocking iterable, but at some point you have reached the limit, right? Things must happen, right? So there is a limit to the speed that an iterable can operate in. And I think, well, I have this intuition that observables have the same limitation. So asking an observable to slow down is not really a natural thing, because in a push model, that doesn't really hold up in reality. Now, what Rx does is, in this situation, well, basically implement a reactive pool model. So basically, asynchronously pool items whenever we want to signal an observable to basically take it a little bit easier. So what is this reactive pool? So like I said, it's really used to signal a fast producing observable to slow down, take it easy. So the important thing of this reactive pool model is that the Rx contract remains unchanged. So the integrity of the emissions is still guaranteed, right? We still know that the emissions will not happen overlapping, and all the other things that we talked about in the contract are still upheld. Now, an important thing is that to notice is that all the buffers that operators use in Rx are now bounded, right? There are no unbounded operators in Rx anymore. So that basically means that we cannot be buffering for infinite items. Now, observe on was one example, but you can think of a zip operator, right, where you zip two observable streams together. Now, if one observable stream is producing much faster than the other one, right, all these events must be buffered to, at some point, be combined with the others, right? So the same problem arises there. And really, this backpressure is not really Rx specific, right? This is really a problem of asynchronous. This is just an asynchronous problem that any asynchronous system will bump into. That is a push based on a push model. So what we do with this reactive pool is we basically request items in chunks, and we request as much as we can handle by this. And these items do not, like, you know, we're not pooling these items because they still get emitted asynchronously, but we get them in chunks. As to signal the observable, this is how much we can handle, and you know, this would be too much. All right. So what this in the code looks like is that we have the subscriber object, which extends observer. That's why I said earlier that, you know, subscriber and observer, when talking, I often use them interchangeably. But what we can do is basically set a producer on an observer, right? So an observer can signal, can basically administrate who is producing the events that it's receiving, and then for this producer, it has this method called request that it can give the number of the size of the chunks that it would like to receive. So for most operators, this has all been taken care of. You don't have to worry about implementing this backpressure manually, but there are some sources that don't do that. So the important thing to realize here is that this solution doesn't really make the problem go away. The problem is still there. We still have a source that is emitting way too quick, and we still have a consumer that isn't able to catch up. So all this solution really does is it moves the problem to a point where we can handle it much better, where we can really handle it in a more nice way. Yeah. Oh, sorry. So what this also entails basically is that we have this mechanism basically gives us control over the flow of the stream of events. So we have this dynamic push and pull mechanism basically to still in this asynchronous setting, request events and control the flow basically. But like I said, not all the sources implement backpressure, right? For example, if you just simply wrap a keypresses event source, right, and then do some observe on that, then that might lead to a missing backpressure exception. Because Rx does signal that, hey, I'm trying to send items to this observer, and you know, I don't have an infinite buffer, so it's not taking them out, so I don't know what to do with these new items because my buffer is full. So what you get in the case that you don't have a source that implements backpressure is a missing backpressure exception. Now, how do we avoid this? How do we avoid backpressure? Because we can, well, one thing is that we can, for example, block on the call stack. And this is maybe a little bit abstract, but most of the time, a lot of the operations that you have, they are asynchronous, but nevertheless, they happen on a single scheduler or a single thread. So that means that the call stack is already blocking basically those the emission of certain events by the observer still trying to process the others. So that is what we call blocking using slowing down using the call stack, by blocking on the call stack. Now that doesn't always hold, like we saw with observe on or with zip. Right, we might be switching to another thread, and then right, the call stack of one observable is not affecting the other, so you don't have this power anymore. So what do we do then? What we could do is calm down the producer stream, and for that there are a lot of operators that you can choose from. And I will just show 2 examples. So this is, for example, a sample. Now let's say you have this observable that is really emitting very fast. Now you might say for certain use cases that you're not actually interested in all the events. You don't really need all of them. You only need the ones that you are, say, that are emitted every, say, 5 seconds or every X duration. Then you can use sample, which takes a duration, and then basically emits the latest event that was emitted on the stream. So this way, we have basically calmed down or transformed a observable that is really emitting quickly to an observable that is emitting steadily on some duration. Now the thing is, obviously, this doesn't hold for all use cases because we're dropping events. Now another operator would be to buffer. So buffer also takes this variation of buffer. So you have a lot of overloads for both sample, buffer, throttle, whatever. But this buffer, for example, takes again a duration. But now what it does is every duration it emits all the events that were emitted within that one duration in a chunk. So there's one emission, gets all these all the buffered elements within the specified time. So we have, and then there are a lot more operators that we could use to slow down or calm a quick fast emitting observable. Now, if we are really interested in not dropping any values because they are really important, like diamonds or whatever, then we could use the on backpressure buffer. Right, so this basically makes sure that all the events get buffered, as long as they fit in memory, obviously, and then emits them whenever the reactive pool mechanism asks for them. Right, so the observer just requests the chunks of some size, and they just get emitted from the buffer whenever necessary. Now another one, again, would be, we have this, we wrap this observable, this source of events, say, key presses, and someone is really pressing quickly. Now, then we're not interested in all of those. So what we could do is, whenever there is back pressure, just drop all the events. Just forget about everything that gets emitted when we're not able to handle it. All right. So, but these are just a sample of the things that you could do. And Rx really gives you the options to apply back pressure for your specific use case. All right. Are there any questions about this?
How does this tie in with the reactive streams?
Well, I'm not an expert on reactive streams, I must honestly say. But as far as I know, reactive streams also implement back pressure. But the thing with the reactive streams is that they basically there is this presentation you can watch given by Eric Meyer, and there he basically derives that it's an asynchronous pool mechanism, basically, the reactive stream. So more or less the same method, but somewhat different. Yes? More questions? No? All right, so let's look at some code for this back pressure. Back pressure. We can stop this. All right, so here is a very simple example of an observable that is really emitting like crazy. Right, just an infinite loop while true, and we just emit this I variable, and we increment it every time, and just keep emitting, keep emitting, keep emitting. Now, as we have seen, observe on must somehow buffer these because we are switching threads. So after the observe on, the thread is switched, and now here we have a subscriber that basically does a sleep for 5 milliseconds. So relatively that's really slow. Okay, so the while loop is going like crazy, maximum speed, and then the other side of the observe on is taking them out relatively slow. So, and then we print the items, and if anything goes wrong, again, for the non-Scala people, this is just, again, a lambda that prints the stack trace. And we do not, I'm not passing in a lambda for the completion event. Now, when I run this, what we see is that all the events get emitted, wait for it, and boom, there it is. Oh, what was that? Ah, missing backpressure exception. And funny thing, it stopped exactly at 1024, which is the default chunk size that the observe on requests. So what happened was, it had buffered these 1024 items, and then the while loop was still pumping in new items. So we were kind of requesting them from the buffer reactively in chunks, but when we hit the buffer, we saw that there was no backpressure. So the exception was thrown. Now what can we do about this? Well, for example, like we said, we could go ahead and sample the stream. So now, let's say we sample every 10th of a second, right? Now, if I run this, we see how quick the while loop was actually increasing. It was all. So we're getting we're sampling the value of the stream every 10th of a second, and now we're not hitting the missing backpressure exception. Backpressure basically has been slowed down, the emitting observable, and here we even see that the integer has been wrapped around because we hit the maximum values for integers. So another option, like we saw, would be to just on backpressure buffer. So that would be just let's try to drop. Now in this case, what would happen is the source observable, starts emitting like crazy. It fills up the buffer that is of size 1024, and after that, everything gets dropped until the subscriber requests a new chunk, right? So we run the backpressure, and what we see is it runs up until 1024, the way we would expect, and then it jumps, because everything was dropping between the time that the buffer was full and then the time that the new chunk was requested. So here we see that on backpressure drop has helped us to avoid the missing backpressure exception. So are there any questions about this? Yes?
Can we modify the buffer size?
Yes, we could by using this producer and the request method. But the default operators, they have the default buffer size. Do I see another question? Yeah?
Maybe I don't understand very well, but in this example, the observable is calling the subscriber on next. So the observable is calling on next method.
The observable is calling on next method? Yes, indeed. No, that is normal. So the observable, we create the observable by passing in a function that takes a subscriber, right, and then does something. Now on this subscriber, we just call on next, right? So the observable, that this on next means that the observable has a value and it propagates that value, or it sends the value to the subscriber, right? Does that make sense? More questions? Yeah? Backpressure on the producer side? Well, yes. I mean, I could add a thread.sleep in the while loop, right? And that would.
Feedback from the consumer to just back off.
Yeah, so that is exactly what we're doing, actually. That is what internally happens. So instead of saying back off, right, what we're saying is, you know what, we cannot handle anymore. So we're not requesting any more chunks, right? And the important thing to stress is that this does not mean that we're pulling every time. We're just telling the producer, you know what, right now we can handle X amount of items, right? And whenever those get handled, then we can again request, and you know, all these items still get passed in asynchronously. Does that answer your question? Yes?
But your producer is still consuming resources.
Indeed. Indeed, yes. But because think about it like this. If you have a mouse event wrapped in an observable, right? You cannot slow the mouse event down, right? The user is just moving that thing and pressing it, right? This is just, like I said, in the general case, this is a very hard problem to solve. And if you ask me, it's really impossible. So indeed, the producer is still doing work, yeah?
Is there a buffer per subscriber?
Is there a buffer per subscriber? Well, no, not exactly. So there is a buffer inside of the operators, for example, right? So because items get through to the operators, but there are certain operators that basically, you know, by using them, this problem arises. For example, zip or observe on. But now, to be able to request chunks from the source, the other operators also must be aware of this, you know, this backpressure situation. So, you know, if it's a chained operator, the last operator says, you know, I can't handle it anymore. He must, you know, signal the other operator, signal this one, signal, and then until the source gets that, you know, message that it needs to slow down. Yeah?
That's good.
Sorry?
Logitech, do they sell a window, a mouse, a Backpressure mouse?
Not that I know of. Would be a nice invention. You can slow down the arm of the user, you know, somehow.
Heat up the mouse.
Yeah, perhaps, or you know, electric shocks or something. Could be. Yes?
Could you demonstrate the implementation of non-backpressure strategy?
Yes?
Like, I don't know, rebound every second.
Sure. That's what I'm saying. So you can use operators. I showed just a couple, but you can mix and match these operators to have another backpressure strategy to just avoid the situation altogether. But if you don't, then you use on backpressure buffer or on backpressure drop, or. And moreover, you have control over these, you know, requesting of chunks and how large you request them and when. So you can really implement your own strategy for that.
And that you would do by using a producer.
Yes. Yeah?
Would it be possible to have some API that tells how the producer should back off if it's possible? I mean,
Well, I don't think so in the general case, like I said, right? Because
I know this somehow you cannot control the click.
yes, yes.
But if the producer have knowledge of how to send
Yes, but then you would solve it on a use case basis, right? And like I said, Rx is really a library, not a framework. So Rx has no opinions, right? Rx doesn't say, you know, we do this situation, handle it in this way, right? It gives you the tools to handle your use case in the way you find appropriate.
But how would you propagate then this thing that the producer should back off? Maybe with another observable?
I'm not sure if I understand the question.
How would you, if the producer can back off because he knows how to back off, how would you do that? Maybe the consumer has to send an observable to the producer?
Perhaps that would be an option.
Isn't it enough to use the producer, I forgot the name of the method, but
On next, or
retrieve, no, there is a producer that retrieve or something like, you should something like
request.
request.
No, that's the subscriber telling the producer, I am ready for X amount of items.
But it's kind of a transparent feedback on the producer saying, well, he hasn't asked me for quite a while, so I need to find a strategy.
Yes. Yeah, I'm not sure if I follow your...
But in some way, the producer not being called for request knows that it should probably slow down its production in one way or another.
There might be an option, but I'm not sure if that's possible. But let's talk about this offline, because this is really an endless discussion about backpressure that is really going back and forth in the community. So the last thing that I want to quickly talk about, because we don't have a lot of time yet left, is debugging, right? And again, debugging is not really an Rx-specific problem. Not that debugging is a problem, but debugging asynchronous programs is really difficult, right? Those bugs are really hard to trace, tend to become quite expensive, and the reason for that is that our current tools that we use for debugging asynchronous programs are really not designed for asynchronous control flow. So, like the call stack doesn't give us any value whatsoever on what is actually happening and why our problems have arisen. So, for example, I'm not sure if everyone is able to see it, but here is a breakpoint that I have placed in a subscribe method, and what we see is like lambda $null, call on next, emit chunk, push value on next, doesn't tell us anything, right? There is no value whatsoever in the call stack. So the traditional debugger really doesn't cut it if you're working asynchronously. And again, this is not just Rx, this is any asynchronous program. So what I'm working on right now is reactive debugging. So first, let's talk about how we would go about print line debugging in a reactive style. Well, what we could do is just add the say we're interested in all the events that get out of the map operator into the filter operator. So what we do is we add the do on each operator in between them and just print everything that gets emitted. So that way we somehow can, print line debug and, get lucky and perhaps find our problem. Now the thing is that, I'm not disputing the power of print line debugging, but this is not, this just takes you up until a certain level. So to quote Eric Meyer, the best way to debug an Rx query is via a second Rx query that observes the first Rx query, or simply avoid bugs. Now, I don't know about you, but I'm not the type of person that can avoid bugs in all cases, so I just have to go with the first option. So what I'm doing is creating a scriptable debugging plugin and API. This is just a front end in IntelliJ. And the essence is really that you can script basically debug sessions. So this is just a small code snippet. For example, you can set a breakpoint, and this event is just an event source of the program that you are running. Say in a class foobar, and set that on line 13. Now you subscribe to this stream. So now every time your program hits that breakpoint, item will be emitted. And what we can do is just check for some value. So we can say get value of, we have a field called state, which has a value x, right? And we know that's an integer value. And then we can inspect that. And even if we want to, we can check if it's according to what we expect. And if not, we can mutate while we're debugging. Now this is a really simple script, obviously, but you can do some interesting stuff with this scriptable debugging. And basically, I don't know if you have seen these things. These are more or less the flame graphs that were invented by Brendan Gregg. And they basically show an aggregated view of your stack trace. So this is like for all the function calls that happened during the execution of your program, they just get aggregated into this flame graph, and you can tell what parts of your code were really in the ancestry of the call stack often. So let me quickly show you how that looks. I have to open another workspace. So if I start this, what happens is this program starts the other program that I'm debugging, and at real time it's catching all the events that are happening, right, reactively, and we're visualizing this by a simple script that makes these call stacks visible. So we can see that, for example, this getDirect method for constant is a lot of the time in the call stack, and now the calls have stopped. Now we see that activity is here. So this gives us a view, but this is just a demo of how you can use scriptable debugging to see what's happening in your asynchronous programs. So let's stop this, and I want to quickly show you how this actually works, because I think that's a nice example of a reactive program. So just look at this expression. This single expression basically does all the work for the creation and displaying these flame graphs. This one expression that gets all the method entries from the debuggee, and then we do some operators, we filter the classes that we're interested in. Then we get all the method events. From that we get all the frames, so we map a function that gets all the frames from every event. And then again we see this scan operator, which takes a empty call stack, so this is actually an accumulated call stack, and then we update that on every event. So here we get the accumulated call stack, and we update that with every new frames that we get from getFrames. Then we sample that because we don't want to be rendering like crazy, we just want to be rendering, say, 60 frames per second, so that we do here. Then we switch to the UI thread, then we map a function, and this is a bit nasty because it's not pure, but it has a side effect. It actually draws the frames and then returns a data structure that contains all the information for the tooltips. We combine that with the events of the mouse, and then we subscribe to that stream to handle the tooltips. And this one single expression does the whole flame graphs, basically. So, all right, that's more or less the scriptable debugging. So, quickly, we have seen the code mostly in RxScala, but I've mentioned that RxScala is really a thin wrapper on top of RxJava, right? And RxJava is really the core of the library that has the actual functionality implemented. RxScala just has this thin wrapper to make the usage of the library language native, basically, to use all the nice features that Scala offers. And the same goes for Groovy, Clojure, Kotlin, and JRuby. They are just very thin wrappers on top of RxJava. So you can use Rx with any of these languages on the JVM. But actually, if you happen to use another language, there is Rx.NET, RxPython, RxC++, JavaScript, and so on and so on. So, and also whenever a new language gets created, you see often that a version of Rx gets implemented. So we can code Rx in basically all the languages. So if you're interested more, this website is really under development, reactivex.io. You can go there for documentation, or visit the GitHub page, inspect the source, and maybe even contribute. And well, if you're interested more in Rx and functional programming, contact us via appliedduality.com. And well, thank you for your attention, and happy hacking.